Yes, sir. So we will see vector for we'll see how long it goes, and we'll solve some problem. And the objective is we want to understand what is a vector, what is a vector quantity, what is resoluting a vector, what is the resolution of vector, what is vertical and horizontal component, and how to find the resultant vector. So this is the objective. Um, Super. Okay. Then no problem. Then we will learn like really nice. Okay. So we'll spend time and then we will learn. Um, yeah, I'll open the syllabus document on my side. Yeah. So now, so it's actually 1.4 in the syllabus. Yes, scalars and vectors. Now, so so I want to recall that we have discussed there are two type of quantities: basic quantities and derived quantities. Yeah. So that's like one attribution. Let's say that we are talking about a person. We are talking whether this person is skinny or obese. Okay, that's a category. Now we are going to talk another category whether this person is tall or short. Okay. So earlier we discussed whether it's basic quantity or derived quantity depend on that's one category. Now we are going to talk about a quantity whether it's a vector or scalar. It's completely depend on other quantity. Yeah. So any combination will work. But basic quantities, none of them they are vectors. They are all scalars. In derived quantity, there are some vectors. There are some scalars. Okay. Mhm. In basic quantity, all the quantities are scalar. Some are scalar. Mm. Okay. So we are going to take so physical quantities. We are going to classify them into two things: scalars and vectors. Okay. The naive definition that we know we learn in IGCS is scalar has only magnitude, vector has magnitude and direction. Magnitude plus direction. So, so this is a very naive definition. The actual mathematical definition is different. The mathematical definition we do not need, but however, I'm going to say it. If you rotate the axioms, if the point change, then it is a vector. If doesn't change, then it is a scalar. This is a mathematical definition, but we do not need that. In case if someone in the future, let's say that you are studying any engineering course, you come across, you can use this dialogue. Okay. Yes. Now, so in general, what is a scalar is even if you change the orientation, whatever the value we are telling will not change. That's a scalar. For example, orientation in the sense direction. Yeah. Okay. Specifically, first let's discuss what is a direction. Okay. So direction involves 2 point. With 1 point, can you tell direction? No, we can't. With respect to what angle you have to tell with respect to a line, right, sir? So with 1 point, we cannot really tell what is the direction. Only at least 2 point. You can tell direction with more than 2 points, but at least 2 point. A reference we need. Okay. Yeah, minimum. So for example, if you are telling angle, you need one line. From that line, you will measure how long it is moving. Okay. Let's say that there is a point A and there will be multiple points. For example, here's a point B, here is a point C, here is a point D. Now we can tell the direction maybe A towards D or towards B or towards C or opposite to B or opposite to C. You can give direction. Okay. Or the most common thing we can give north, south, what is this? East, west. So we can give like this. Or simply we can give a coordinate in the graph. All this conveys the message of direction. Okay. Now, what do we mean by scalars has only magnitude is if you change or disturb the direction, the values really will not change. For example, let's say that I want to measure a temperature of particular object. Okay, assume that this object is not a liquid; it's a solid object, and this can hold the thermometer very well in space. Okay, now whether the does the object cares whether you are measuring upside down or downside up? No. So even if you are changing the direction, the temperature is not going to change. So temperature is a scalar quantity. Okay. Now let's take mm, quantity values is not going to change. It will not change. Okay. So here comes other example. Let's say that a mass of an object. By definition, what is mass? Amount of quantity, amount of property that has occupied space. Matter. It's a matter. Depend on what angle you are looking, the mass is going to change. It based on the object. It is based on the object. How much matter has occupied space? Is it going to change how you are looking it? Which from which angle you are looking it, or from which direction we are looking it? No. So mass is a scalar quantity. Okay. So we will scalar and vector. Okay. So we have established mass is a scalar. Uh, Time scalar. Okay. So actually, whether time is a scalar or vector in IGCSE or ASA level, it is very easy to address. But in relativistic level, it's not easy to address. Okay. Yeah. So length we will discuss because we will discuss two type of length, whether it's a displacement or distance. Okay. Uh, Now let's take speed. In the car, we are seeing speedometer, right? So does the speedometer concern about which direction we are going? Okay. Whether we are going from A to B or B to A, it will show the actual speed. So speed is a scalar, but his counterpart velocity is a vector. How velocity is a vector? You should ask. Yes. Hmm. Why velocity is a vector is velocity is speed in particular direction. Yes. Okay. But we will see why velocity is a vector in detail when we discuss second chapter. Okay. So there we will address this question. So like this, current is a scalar, mole is a scalar, light intensity is a scalar, pressure is a scalar. Okay. Now, 1 minute, sir. Okay. So now what few people make mistake is, let's take the case of pressure. Pressure, we know that formula for pressure is force by area. Okay, we know that force. Okay, force is a vector. So they assume pressure is also vector. No, even if one of the quantity in your equation is a vector, it need not to be a vector quantity what you are deriving. Now that also will explain. Okay, for example, let's take okay. So first I list out all the quantities that are scalars. So current is a scalar, resistance, capacitance, what else in basic, energy, uh, from then temperature we have already wrote. No, temperature. So there are actually many scalar quantities, but in our list, density is a scalar quantity. Volume is a scalar quantity. Charge is a scalar quantity. Area is a scalar quantity. But there is something called areal vector. Yes. Okay. Let's say that this paper is oriented in this way. I want you to tell you like which towards which direction this is oriented. So I will use the normal to this. So this is its direction. So if I lift the paper, aerial vector. Okay, see, as I change the paper angle, can you see that the angle it points change? So it's aerial vector. It's very important in magnetic field. Okay, so now let's pay attention to vector. Displacement is a vector. Okay, we will see what is displacement and distance difference in next chapter. Acceleration is vector. Momentum is vector. Um, force is a vector. Weight is a vector. Upthrust, if you take force as a vector, once you define a force as a vector, it doesn't matter whatever the force, all the forces are vector. Yes, it can be thrust, it can be tension, it can be upthrust, it can be air resistance, because they depend on direction, right? Okay, but if you take magnitude of air resistance, it's a scalar. In general, it's a force. This force act in the opposite direction, so it carries information about the direction. So it is a vector. Okay, and any field is a vector. So yeah, so any field, it can be gravitational field, electric field, magnetic field. Okay, Higgs field, there is something called Higgs field, that is also vector, any field. Okay, Higgs field is have you heard Higgs boson? Okay, no problem. It's associated with that field. Okay, so any field is a vector. Now, so two things we should remember from the list is that even if a quantity, for example, pressure is force by area, force is a vector, but pressure is a scalar. Okay, similarly, if you take energy, it is force into displacement. Both of the quantities are vector, but energy is still like scalar. So how we will see? So we will learn when we learn it. Okay, is it clear? Yes, sir. So these are the list of scalar and vector quantities, not limited to the full list. So I just gave you the list, but it's summoned to, yeah. As we learn the syllabus on upon each quantity, we will discuss whether it's a vector or scalar. Okay, there is something called a pseudo vector, but we do not need to worry about it. Pseudo means it act like a vector, but it is not a vector. Pseudo means um, what is the meaning of pseudo? It it's not real, but it act like real one. Okay, so pseudo vector means they, yes, it's not pretending, but they act like they carry the direction information, but really they are not. But they are actually carry a few information. Yes. Okay. So, but that's not, we do not need that one. Maybe if you go to engineering mathematics, then you will learn pseudo vector. Okay. So this is scalar and vector quantities. Definitely they'll ask one question: circle all the scalar quantities, or circle all the vector quantities, or how many vector quantities from the list. You should able to give the answer. Yeah, because one, it's very easy to find, because the list of scalar and quantities, vector quantities we have in the syllabus is very limited. So once you finish AS level, for example, we will learn something called wavelength. Wavelength is a vector. So frequency is a vector. So whenever we come across a quantity, we will add it to the list whether it's a scalar or vector. So when we end the syllabus, you will have a complete picture. What are the number of scalar quantities? What are the number of vector quantities? So that, no, you can understand whether when we discuss a quantity, you can clearly understand whether it's a vector or scalar. Okay, all the quantities we will discuss. Yes, sir. Is it clear? Yeah, super. Okay. Now, now let's jump to this vector calculation. Okay. So in the vector calculation, there are two major ways how to represent a vector. Okay. So one is graphically, another one is numerically. Also, you can mention vector, but we don't. I don't know why AS physics doesn't carry how to handle the vector numerically graph. Okay. So we have only graphical representation of vector. Okay. So now a vector is denoted by an arrow. Okay. Now, uh, in this arrow, the length of the arrow is called magnitude. Okay. And the orientation of the arrow is called the direction. Okay. So whether it's oriented this way or this way or this way. Okay. And this arrow has two parts. This one is called tail, and this one is called head. Okay. Yes. Now, direction is given in multiple way. You can tell whether it's, maybe you can tell a vector generally north direction or south direction or west direction, east direction, something like that. Or this is a graph x and y. Okay, let's say that I'm drawing a line here like this. In this case, direction is what is the angle you are making with the x-axis. That's your direction. So what is the angle the arrow mark make with the x-axis? That's your direction. Okay, from this we can get useful information. For example, uh, yeah, same line. No, oh, sorry, I tried to draw the same line, but it went little away. Yeah, yeah, yeah. Okay. Now, so this quantity we call it as a, let's say, let's name this vector r. Okay. So now maybe vector is for v. Okay, capital V, and I have to draw arrow mark to represent this as a vector. In books, it's given bold letter or it will be given arrow mark. Mm. Okay. Now, this part here is called what is the length of the vector in x-axis, right? Okay. Uh, so this is called Vx length. Okay. Now this is what is the vector's length in y, right? So this is Vy. So now what is the Pythagoras theorem? Yes. So the hypotenuse, yes. Mm, yes. So hypotenuse square is a square plus b square. So in this case, v square is equal to vx square plus vy square. But we want only v. So it will be square root of vx square plus vy square. So v and vx and vy are just for representation. Then this v is what we call it as a magnitude of the vector or length of the vector. Okay. Yes. Then how to find the direction? Yes. Now let's take the same quantity. Okay. Now this is a theta and this is vx and this is vy. They are nothing but x component of the vector and y component of the vector. Okay. Now what is tan theta? Or tell me in hypotenuse opposite adjacent. Three. Tan theta is opposite by adjacent. So if theta is here, this is opposite. theta is here, this is opposite. Okay, now we are working with theta here. So opposite is whichever way here. No, you can take here also. Anywhere you can take. Anywhere you can take. Only you can't take this here because it's a perpendicular. And opposite to this is hypotenuse. Okay, you should take any degree where hypotenuse is involved. From there you can take any angle. It'll work. Whichever side you're connected to your angle is adjacent. Whichever side is not connected to your angle is opposite. That's all. Okay. Now tan theta is opposite. What is opposite length? Vy divided by opposite is Vx. So now we want angle. So angle is tan inverse of opposite by adjacent, or Vy by Vx, or xy by, sorry, x value by y value. Sorry, y value by x value. This is how we find, that's a how we find angle. Mm. Yes, yes. Mm. Mm. Yes. Mm. Yes. Mm. Yeah, that also we'll solve. Don't worry. We'll have. Okay, sir. Yes. So is it clear so far? Yes. Super. So we'll do small problems. Now, let's take a vector, okay, where its x quantity is moon. Uh, okay, 3. Y quantity is also 3. Find the angle it makes with the x-axis. How you will figure out? What is the angle it makes us with x-axis? No need to go to Python. Okay. First find the length of the vector. For angle, you do not need to use Pythagoras theorem. But since you started, find the length of the vector. Yes, exactly. So if I want the length, let's say that this is r vector. If I want the length, r is square root of 3 square plus 3 square. So 9 plus 9, 18. Yes. So r will be 4.24. If it's a velocity, we will call it meter per second. If it is force, we will call it a Newton. That doesn't matter. Here, we don't care about that. Okay. Now, what's the question? What is the angle? Now, we had two things. Okay. X part is 3. Y part is also 3. We know that theta is tan inverse of opposite by adjacent. In this case, 3 by 3. Tan inverse of 1. Yes. So, tan inverse of 1 is 45 degree. So, let's take another vector whose x-axis is 5, y-axis is 5. What will be the angle? So, length will be again root 50. Okay. Then, okay, no problem. Angle? You do not need to calculate because we know that theta is tan inverse of again 5 by 5. So the angle will be 45 degree. By the way, how to work tan inverse is, we'll open this one. Press, make sure it's in degree mode. So 45 degree. So if you take any vector whose x-axis value, horizontal value is equal to vertical value, it will always have the angle of 45 degree. Okay, it makes sense, right, sir? How much you went in x-axis, same amount you went in y-axis. So you will have only 45 degree. Okay. Yeah. So can I assume that you understand how to find the magnitude and angle of the vector? Yes. Now we will learn something about what we can do with vector. So this is called the vector calculus, but very basic. Maybe Papa vector calculus. We can call it like that. Okay. Now first, if I have a vector, okay. Now let's say that this is my vector. Okay. Now uh, this indicates the head part of the vector. This indicates the tail part of the vector. Okay. Without, now I can do two things. I can rotate like this. Okay. Wow. This means I'm changing the angle. Okay. This we cannot do to a vector without some vector is adding or subtracting. There is a vector like this. Now it has some angle, right? Now let's say that this is the vector. You cannot twist the vector like this, meaning we cannot change the angle. But what I can do, let's say that this is a vector. I can simply multiply it by 2. So this will become like this, twice the length. This I can do. So this is called scalar multiplication. Why scalar? Direction is not changed. 2 is a scalar. 2 is a number. We are multiplying by a scalar, so it's a scalar multiplication. That's all. Okay. Question, sir. So when we discuss the resultant part, you will understand. Mm. Okay, sir. Now, now let's take the same vector. Now here is a vector like it, right? I cannot change the direction. Without changing the direction, I can move it like this. Now this is the same vector. Same vector, that's all. I can move it without changing direction. This one property helps us to resolve most of the vector problems. Okay. Now, yes, you can move actually. If this is a vector, you can move left, right, up and down without changing the angle. You can move it anywhere in the page. This page is called a plane, right? Let's take this a plane. Okay, here is a vector and here is another vector. Can I call it home of these two vectors or this plane? So these two vectors are called coplanar vectors. So they are called coplanar vector. What's the definition? They should lie in a same plane. Okay. Now let's say one vector is like this. If another vector is like this, can you tell they are coplanar vector? No, because the second vector is in different plane. Yes, different angle doesn't matter. Now, if they are like this, then we can call them coplanar vector because they are in same plane. This is coming out of plane, so we don't accept this as a coplanar vector. Same way for going in also. Yes. Okay, sir. So why this understanding is very important? What we are learning in AS level is only two-dimensional vector. So it will be easy for us to add and subtract. So given our syllabus limitation, we can add and subtract only two-dimensional vectors. In reality, you can add and subtract any dimension vector. Yes. That's why this coplanar is very interesting. Okay. Okay. Yes, sir. Now what is now this is A vector, let's say. Now if you turn the vector 180-degree, then we call that as a minus A vector. Yes. So turn a vector 180-degree, then A vector becomes minus A vector, any vector for that matter. This is also a useful result. Okay, sir. So for our MCQ and theory questions, this understanding is more than enough in vector. Okay, but if you are interested further, there are in calculus called vector product, dot product, and cross product. I think it's there in mathematics. AS mathematics is not maybe. Okay, okay, we'll check on it. Maybe A level mathematics. I am not sure. Okay, yes, sir. Now, what we have to understand is what is a resultant vector. Okay. Now the vectors are subjective to add and subtract with the same plane as far as we discuss. Okay. Add and subtract. So a new direction will form. Okay. This works only with vector. Definitely it will change. Okay. Now a very good example is force is a vector. Okay. Let's say that here is one person, person A, and person B is pulling this person A in this direction. So person A will move in this direction, right? Okay. Now let's take the same person A. Person C is pulling in this direction. Okay. So this person A will move in this direction. So far, so good. No problem. But when the same case, maybe we'll take it case 1 and this is case 2. In case 3, same person A. Yeah. B is pulling in this way. C is pulling in this way. Which way person will be moving? So he'll be moving in this one. So this is what we call it as a resultant vector. This resultant vector is nothing but, let's say maybe resultant vector, we call it D. D is nothing but B plus C. Okay, and it has this additive product. So B plus C or C plus B, both are same. So A plus B is B plus C. Sorry, B plus C. Okay. But remember, nobody is pulling in this direction. Yes. Okay. Now we'll look at what happened here, why this person is going in this way. Yeah, sure. Yes, sorry. Yes. Now we are going to understand something called horizontal and vertical. Okay. So first, what is your understanding of what is horizontal and what is vertical? Yeah. Okay. Yes. So sometimes people forget. So I'm going to draw the line. So this is horizontal. Okay. And this is vertical. Now each each vector can be splitted into these two components. Yes. Any vector. Okay. So for example, let's say that this vector is this. So how I'm going to define this vector is you start from this point, walk horizontally like this. So walk horizontally certain distance and take a 90-degree turn and walk certain distance, this distance. So you will arrive. So this I'm going to call horizontal component or AX. Remember, this I'm going to call vertical component. So AY. So if I add, if I let's assume if I have two vector AX and AY, then their resultant will be this vector. So we are just splitting this vector into horizontal and vertical components. That's all. And whatever we are splitting, the angle must be 90-degree between them. This is a no, no, we will see, we'll see. Okay, can you see if this person is here, one is pulled here, one is pulled here, obviously he will move. So this, if you split, you will get this and this. Okay, that's what we call it as a resolution of vector. Okay, so this resolution of vectors helps in many places. Okay, for example, let's take the example we discussed earlier. This B is pulling in this direction, C is pulling in this direction, right? Now we'll split B in 90-degree components. Okay, so one is going to go here, another one is going to go here. So can you see the angle between them is 90-degree? So I'm going to call this as B horizontal, and this I'm going to call it as B vertical. No, it depends on orientation. The what we care is angle between the horizontal component and vertical component is only 90-degree. We don't care about what's the angle between this or this. This will be theta actually. Hmm. Yeah, it will be 45 only if you split them equally half. Okay. Now I'm going to split this C also into horizontal and vertical. Okay. Now we are going to call this as C horizontal and C vertical. So can you see that CH and BH, they are equal and opposite? So what they will do? If there is a place, you are pulling here and I am pulling here. What, where, with equal amount of force, where it will move? So they will cancel out. Okay. Now what will happen to BV and CV? So BV and CV is what we call it as a resultant force. Yes. Okay, sir. And it is very important to resolute this vector to get useful results. Okay. Now let's solve small problem. Uh, I know I think you know this equation. Force is mass into acceleration. Hmm? Now, let's say that there is a train. Okay. I am pulling this train like this. Sir, I also want you to remember that this train is on rails. So it can't go left and right. It can just go forward and backward. Now, if I pull in this direction, which direction the train will move? Obviously towards this direction. Okay. Now, for our easy case, let's take mass of the train is 100 kg. I am pulling with force of maybe let's say 100 Newton. Find me the acceleration of the train. So acceleration is, we know that force by mass. So it will be 100 by 100. So 1 meter per second square. So the train will accelerate with 1 meter per second square in this direction. Okay. Now the tracks are like this. Same train is like this. I am pulling here with 100 Newton. What will be the acceleration of the train? In which direction I am asking acceleration? Yeah. Am I pulling, or is this force enough to topple the train? No. So obviously train can move only in this direction. No, but will the train move at all? Why? Yeah. So, but in this case, we are spending all the 90-degree. I am pulling train in 90-degree with 100 Newton force. Will it accelerate? Why? Why it will not? How it will accelerate? What force is causing the acceleration? Let's say it's just a cart, no engine. Then it will not accelerate because all my force is perpendicular, right? Hmm. Yes. Hmm. Why? This vector has no horizontal component. Hmm. So acceleration is zero. So horizontal component of the force is zero. Now let's do the same example with this side. No, but it cannot move it in left and right, right? It can move it in up and down, but the train doesn't have freedom to move up and down. Uh, it will be stationary, and the force will be converted into the thermal energy in the tension of the wire, tension of the rope, whatever you are pulling it. Okay. Now let's say that I am pulling this rope with 30-degree with same force, 100 Newton. Now, what is the acceleration of the train? That's the question. So first we have to find the force horizontal. How we will find the force horizontal? Mm. Yes. Mm. Mm. Adjacent. Is it opposite 100? Really? What do we need is horizontal force. Okay. So this we need to split into horizontal and vertical. Can I just break it like this? What is the condition? The angle between the horizontal component and the vertical component must be 90-degree. Is it true? Yes. Now I am interested in horizontal component. So which degree? Degree, is it next to degree or opposite to degree? No, no. What we are interested in? FH, which is next to degree or opposite to degree? Angle. Next to. Okay. So we'll take cos. That also we can do. Okay. Now cos theta is adjacent by hypotenuse by adjacent or adjacent by hypotenuse. Yeah. Uh, So adjacent is hypotenuse into cos 30 degree. So this will be 100 into cos 30. So if you take cos 30 degree is 0.866 multiplied by 100, you will get 86 Newton. So you will give your force, your horizontal component of the force is 86 Newton. Divided by mass of the train, it will move with acceleration of 0.86 meter per second square. Yes. Okay. Is it clear? Uh, you want to make a note or can you turn the page? Yes, sir. Sure. Yes, super. Now, so if a vector is like this, okay, and making an angle with this line. Now, this case, this is our reference line. Okay. So now we want to find this horizontal component and vertical component, which means we want to find this and this. So this we can move it here. Can you see that this and this are equal? So this will become, if my hypotenuse is, let's say, x. If my hypotenuse is x, this will become x cos theta. This will become x sin theta. Mm. Yes, no problem. Okay, so I'll draw it a little bigger. If this is theta, okay. So now we want to find horizontal component and vertical component. So can you see the angle between horizontal component and vertical component is 90 degree? Okay. Now I want to move this vertical component here. So this and this is same. Now this is adjacent part. This is opposite part. This is hypotenuse part. So what we are doing is we are splitting the hypotenuse into horizontal and vertical component. Okay. Now it's a triangle. This is adjacent, provided the angle is here. This is opposite. This is hypotenuse. So we know that cos theta is adjacent by hypotenuse. So adjacent is cos into hypotenuse. Similarly, opposite is sine into hypotenuse, right? Now let's take hypotenuse is x. So adjacent will be x cos theta. Opposite will be x sin theta. Okay, is it clear? But how do we choose? Someone will draw like this also, right? But problem is this is the angle between your vector and one of the vector. What is the condition? Horizontal part and vertical part should have 90 degree, not your vector and one of your vector. Hmm. Yes, you can. Yes, yes. Still, you will get the same answer. Okay. So, very good question. So, let's say that this is theta, and I'm interested in vertical component and a horizontal component. So, what I'm going to do, instead of moving this component here, I'm going to move this component here. This is what you're asking, right? Now, this is theta. This will be 90 minus theta, or this will be theta. Okay. So, this is a z. So, this will be theta. Now, if you look, this will be opposite. This will be adjacent. So, x cos theta, x sin theta. Is it clear? Super. Okay. Uh, Now, let's see some problems. We'll use some problems. Okay. Uh, Now, let's say, yes, sir. Okay. Now, let's take a simple pendulum. When it is simply hanging, there is only one force acting. What is that force? So, mg is in this direction. Okay. Wow. But let's say that let's lift this simple pendulum to some distance. Now, in which direction mg is acting? Downward only. Okay. So, mg. Hmm? In which direction the pendulum moves actually? Can you say it moves like this? Okay. Now, this is the string. Now, I'll call you like, okay, we'll call it. If the string is weak, can this hold the pendulum? So, it has to hold, otherwise, it will snap. So, there is a force tension in the string. So, two forces are acting, one tension, another one is mg. But how it is any of the force in this direction? Then why they are going in this direction? But what's the origin? Obviously, we are not pushing it or pulling it. Initially, we did, then it is going on its own. Okay, so to understand that, now this is a tension, right? Now this is angle theta. Hmm? Now this is W, mg, or we'll call it W. W for weight. Okay, wow. So can you see it's equal and opposite to W? You tell me. Yes, sir. Uh, Close. Okay. Are you ready? That's vertical component of the tension. Of the tension, T. Okay. Yes. Okay. Horizontal will be acting this way. No, actually, this is too perfect. It will act like this slightly. In this line, actually, it will like. No, yeah, it's close. I'm just exaggerating in the figure. Okay. Yeah. Now, let's zoom in and we'll see what happens. So here is the bob. It looked like this. Here is mg or w. This is t. Okay. Now, if the angle between this is theta, this is also theta. Okay. So now this is w. So the w will also have vertical and horizontal component. Okay. So w also can be Okay. So now if this is theta, this is also theta. Let's say that I am moving it here. This one I am going to move it here. Okay. Now this is opposite. So this will be W sine theta. If this is a W sine theta, this is same as this is what we moved here, right? So this is W sine theta. What is it? Yeah, this will be W cos theta. Similarly, so this is T. I'm going to move the horizontal component of the T here. Okay, so this horizontal component of the T will be somewhere here, right? So that I will move it here. No, actually horizontal component will look like this. Okay, this I will move it here. So the horizontal component of T will be this T sine theta. The vertical component of the T will be here T cos theta. So T cos theta will balance W. W cos theta will balance T. Okay. If this is the case, the simple pendulum is in equilibrium. Yes. So the pendulum will not move. It will just stay there because it's exactly matching, right? So when the pendulum will move, the T's vertical component is cancelled and T's horizontal component remained. So then it will, and but the beauty is this is not a constant part. This depends on angle. It will change. Okay. So if you take this position of the pendulum, T is exactly equal to W. Okay. If you take this component of the pendulum, no T, only W. So if you, let's say that if it's going here, this is where inertia will work, W will work. So a small angle. So this depend on the position. So depend on where and what condition we will split it. Okay. So this is very easy. Once we solve the problem, it will be very easy. Yes. So we'll do one more problem. You will see right through it how to solve this problem. Okay. Can I just turn back and then you can note it again? Okay. Super. Can I change page? Yes. Okay. Now this is a very interesting problem. So now let's take a slide, and here is one bar mass. Okay. Obviously it will slide down. Why it is sliding down? Yeah. So it's theta. Now some force must act in this direction, right? So this is W. This is W. And this is how the normal force will look. You know what is normal force, sir? Yes. So if there is no normal, this object would have embedded into the slope. Okay. So we have to split this W in terms of, yes, contact force. So we have to split the W in terms of its horizontal component and vertical component. Okay. Remember, this is the theta. So if this is the theta, this is also the theta. Okay. So there, 1 minute. I'll take some sharp edges, for example. Okay. No, this is not suitable one. 1 minute, sir. I'll open the simulation. It they have the simulation with the spring. They don't have simulation without the spring. Okay, no problem. Yes, sir. 1 minute. 1 minute. Yes. Okay. Now, um, if this is the triangle, and you can see that this triangle is actually similar to this triangle. If you take it, yes, if you take it and slide it by 90 degree, will these two are equal. Okay. So because if you draw a horizontal line, if you draw a horizontal line, okay, so this will meet here, right? So this angle is this angle, right, sir? And if you tilt this 90 degree, you will reach here. So this will be also same 90 degree. Sorry, same theta. Yes. Okay, so I'll draw a clear picture. So if this is theta, this W, this is also theta. Okay. Now W, we are going to split into these two components. Either you can move it here or you can move it here. Okay, here is W. So here is theta. Okay. So yes. No, no. Finding theta is just mathematical part. Okay. Now this is opposite, right? This is opposite. So this is mg sine theta. This is mg cos theta. Mm. Most of the cases, yes. But this depend on the angle also. Yes. Mm. Okay. Now if there is friction, friction will be counterparting the mg sine theta. So normal force will be counteracted with the mg cos theta part. Okay. So n is mg cos theta. If there is friction, but we don't worry about friction now. So the mass will experience force of mg sin theta. If it is 30 degree, and this guy is, let's say, 1 kg, then the acceleration will be force by mass. So which is 1 kg into 10 meter per second square into sine 30 degree divided by 1 kg. So you will get 10 into sine 30. Uh, Sine 30 into 10. Mm. So you will move with 5 meter per second square. Okay. So as the angle increase, sine theta, sine 0 is 0, sine 90 is maximum, right? So put the here, put sine 90 degree. Then what you will get? 100. Why? Because if you put sine 90 means slope is like this. No, no, sine 90 is 1. Yeah, sine 90 is 1. So it means slope is almost vertical. So you will be falling like free fall. If you put sine 1 degree, then the slope will be look like this. Yes. Okay. So if you increase until certain angle, the slope will stay until the friction gives out. where the friction will give out, you can easily find. Okay, this is a problem. Okay, sir. Acceleration of the box. We are finding acceleration. Yeah. Okay. Yes. Yes, sir. Now we will go to resultant vectors. How to find resultant vectors? So this will give more idea. Okay. Now let's say that this is A vector and here is B vector. So we want to find the A vector plus B vector. So how to find this? Move the B vector without changing the direction. Tail of the, okay, first you can select any one vector and leave it there. Okay, let's say that I selected A vector. Second, take the other vector without changing the direction. Tail of the second vector should come to the head of the first vector. Okay, so we will take this B vector and we will place it here. Sorry. Okay. Third, connect tail of the first vector to, this word is very important. You should go from tail to head. Yeah, head of second vector. So this is what you call it as A vector plus B vector. Okay, they can be in any orientation. Okay, sometimes, yes, yes. So the same problem I'll give like this. See, A vector is in this direction, B vector is in this direction. Find the resultant vector, they'll ask. Simply take the B, put it here, find the resultant vector, that's all. Okay. Do you remember your board problem and water problem look like this? Yes. So just take the arrow without changing the direction, put it there, that's all. Okay. Yes, sir, is it clear? Yes. Mm. 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 No, we will talk about minus vector. Okay. So your question is right, but we will cover it here, hopefully. Okay. See, let's see. Sir, do you understand until this, sir? Yes. Okay. Now this is A vector plus B vector. Now we will do for one more vector. Okay. Here is A vector. Here is B vector. Find A plus B. Yes. So this will be A plus B vector. Okay. So how we are moving the vector is very important. Okay. So this is problem 3, I guess. Then you will be wrong. You will be right actually. Okay. This problem you are asking. Yeah, you will be right. Okay. I thought you are asking this. This is also you can do. Okay. Keep the B vector. Okay. This is your first vector. Keep the A vector and just draw the line directly. This and this will be same. So A vector plus B vector. Okay. Not a problem. Good. But luckily it was, sometime it will be given like this. So A vector and B vector. Now we should not connect line. Yes. Yes. So I can do, take B vector, move the A vector here and connect this. Okay, sir. Now, little tough question. Okay. Now here is A vector. Okay. Now here is A plus B vector. How B vector will look like? Yes. You understand the question, sir? Super. Mm. Mm. Super. Awesome. Yes. So super. So first point is tail of A vector and tail of A vector plus B vector should have meet. Okay. So this is A vector and this is A plus B vector. So in which direction B vector should have gone is this. So this is B vector. Okay. Have you seen this type of question, sir? Question papers? Oh, really? But this is exclusive in 9702. Yeah. Okay. Okay. No problem. Okay. Can we solve one more problem? Why it is wrong, sir? Okay. So how to check whether this is right or wrong? Okay. Now let's say that I give you A vector is like this. So B vector is like this. Find A plus B vector. B is this. Mm. Yeah. So A vector is here. B vector is here. So this is A plus B. Isn't this the same thing that we have drawn here? Here, this is error mark here. B is this. So remember, when we add two vectors, the resultant vector's head will meet with the second vector's head. A is this. We don't change the direction of the A. Why you want to change? Show me, show me, show me what you are. Hmm. Yes. Ah, super. We are not, what you are talking about is adding A vector and A plus B vector. Okay, but we are not adding A vector and A plus B vector. The question is, if A vector is this, A plus B vector is this, then what is B vector? Yeah, no problem. Is it clear now? Super. Mm. I see. I see. Okay. Okay. Mm. Yeah. Now is it clear, sir? Mm. Yes. Is it clear? Mm. Yeah. So now we can go a little further and ask this question. Let's say that here is a point. Two forces are acting, A vector and B vector. Okay. What is the vector that has to act so that this object is in equilibrium? So there are four options. Okay. Now let's say that this is option A, this is option B, this is option C, this is maybe mm, this is option D. Which one? What is the question? Equilibrium. Super. What do you mean by equilibrium? Yes. 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 So which vector is this? Yeah. Super. Why? Mm, awesome. Super. The resultant vector is in this direction. If there is no other vector, the object will move in this direction. To counteract, we should give vector in this direction such a way so the, these vectors are in equilibrium. Okay, is it clear? Super, sir. So there is one more difficult question that I saw. Actually, many more. We'll see how it can. Do you have any test or exam tomorrow, sir? Okay. Maybe we'll finish two or three questions. Yeah. QP1. Yes. Super. Yes, sir. Okay, we'll finish this and then ask. Yeah. Super. Okay. Okay. Sir, here's the question. So this question is actually 970212MJ13. Okay, so here is a diagram. Yes, sir. So here is 4 Newton and here is 3 Newton. Two forces, yeah, it's a sphere. Two forces act on a circular disk as shown. Which diagram shows the line of action of the resultant force? Okay, this is a question. So A is this 5 Newton. So B is this 5 Newton. C is this. So this is little horizontal, right, sir? So this is like this 5 Newton. D is this, not in the center, 5 Newton. What's answer? So in A, it is slightly toward horizontal. In C, it is exactly 45 degree. Yeah, why? Super. Mm, mm, mm. Yes. Mm. So resultant will be closer to 4 Newton. Okay, where the forces meet. 3 Newton will we can move it here. So it will be close to 4 Newton. Right answer. Super. Okay. Uh, ah, okay. So this one you can answer, sir. This one is S13 QP13. Okay, question number 1. This is question number 3. Okay. So this is 5 kilometer. This is 53 degree. This is a displacement we are talking about. Question is, what is the vertical component of the displacement? So you did 5 into sine 53, sir? Yes. Mm. So it's supposed to be 3.99, 4 kilometer. Mm. So this is 4 kilometer. Or you can do the same problem like this also. Okay. This is 53. They're asking for the vertical component. So this will be 90 minus 53. But this is okay. Now you can do cos 37. 5 cos 37. Same answer. Okay. Yes, sir. So there are some resultant vector questions. I'll send you a PDF. We can solve. We'll see if you have any doubt. In that one, we'll solve it tomorrow. Okay. Yes, sir. Now you said you have some doubt in which one, sir? Mm.